Is that?
Get that on there?
Yeah. Hell yeah.
Minus u
But it's a good estimate.
plus x squared 0 for 0x 1.
Yeah,
So,
I'll take hand notes.
subject to two boundaries.
I'll take hand notes if you want to take the
0 is
fat lab. You know, that's
0 and 1 is
what do I do?
Just hold it there. So it's a pretty simple differential equation. Really, it's you've seen this a lot. Negative u double prime minus u equals negative x squared. The problem with it is that the boundary conditions that they give you are not. They give you a value and another value. Usually, you're expected to be given a value and a derivative. That way, when you're trying your sines and cosines, you can figure out what is the homogeneous for a particular solution. So you're kind of screwed over here. So in this class, we're learning how to solve this using the finite element method. So the general idea, I'm going to kind of go back to very few lectures because you guys are struggling with this. So what you do when you have an equation like this, right? You want to multiply the equation through by some weighting function w. Just hit both sides with w. So you say w d squared u dx minus w u plus w x squared equals 0. And once you've done that, you also want to integrate the whole thing from one x to another x. Say to x b. And the whole thing is, of course, with respect to dx. So what you do, now we're setting ourselves up for a finite element problem. We don't want to find a solution for the whole domain because that is just complicated. I have no idea what kind of function goes from 0 to 1 that satisfies this condition. So what we're going to do, we're going to actually split our computational domain into mesh. We're going to mesh it and split it into elements. So let this be 0, let this be 1, and let's have a bunch of nodes.
It's not partial derivative,
I mean, let's call it partial, doesn't matter.
It doesn't matter anyway.
Yeah, right now because it's only a function of u and x.
Yeah.
This was also like a function of t that doesn't matter. We'll keep it as a partial for now. So you mesh this up in the domain, so I'm going to find a solution that satisfies this chunk of domain, the one from. What's 1 divided by 4? Quarter. So this is so I'm going to find a solution that goes from here to there, then I'm going to find another solution that works from here to there, and then another solution that works from here to there. That's going to be much simpler. So that's the general idea. And so to do that, we take our first original equation, the one that we just hit by the weighting function w. We're going to integrate this by parts. The idea is that every time you integrate by parts, you are making this term to be a derivative, and this term you're freeing, you trade the derivatives essentially. So if you look at just at this portion right here, just take the dumb integral from b w. Let's just evaluate this chunk by parts. Let's see what it is. So pull out the negative sign. Let this be u, let this be. So this is my u, this is my dv. The rule is uv minus v du, so that becomes w times this times du dx.
I think I may copy those notes.
Minus integral goes from say minus v du, Okay, so in the first integration by parts right off the bat, you can see that you've turned this second derivative of u into a single derivative of u, but by doing that you made the limit, you got this weighting function up here as a derivative. And if you integrate this term by parts again, so just let's keep this as is.
Wait, shouldn't that just be du df, not d squared du?
Yes, very good, thank you. So it's going to be plus integral u double minus u v minus
You need to do it here.
yeah, you can yeah.
I just thought you were going to, they were the same derivatives.
Ah,
It should be.
yeah, actually, yeah, you're right. Yeah, you're right. In this method, we don't need to do it again. So, okay. So this thing right here,
I think we're going to.
you usually know what it is. That's given by the boundary condition. Now, let me explain what XMX means. So, right now, what we're trying to do, we're trying to find a solution that goes for a specific element. So, with these nodes right here, you got 4 elements, 1, 2, 3, and 4, right? And every element goes from XA to XB. So that becomes XA and XB for element 1. For element 2, that's your XA, that's your XB. For element 3, that's your XA, that's your XB. For element 4, that's your XA, that's your XB. Is everybody okay so far? Please, if not, just stop me because I'm trying to kind of rush through this. All right, so that is what's happening here. And
Does that make it plus in the middle too?
plus where? Here?
Yeah.
Well, minus, plus. So yeah.
Oh, you have it all the way.
Yeah, I kept the minus sign. So when your next step is actually to actually find the solution. So now you need something called interpolation functions. You want to for any point between these 2 points, you want to find a solution if you're given what the XA and XB are. So you have a few ways to go about this. You can use a D1 interpolation and you can use a D2 interpolation. So you can say, in mathematics you can always suppose. You can suppose that your solution at the element all goes as like this. So it's a first order polynomial, right? So let's say, all right. You can say, well, let's plug in XA into here. So say U of XA of any element is going to be then C1 plus C2 times XA. And similarly, plug in XB in this equation to get this. Okay, everybody's good so far? Very simple. Now, what we want to do, we want to put this thing in a matrix form so that we can solve for C1 and C2. So, 1 XA, 1 XB, C1, C2 equals
We know XA and U of XA and U of XB?
yes, we'll know this.
Those
So-
are boundary conditions?
Right. So far so good, everybody? I got from here to there. I just put this in the matrix form. Now, using something called Kramer's rule or whatever your favorite technique, you can actually solve for C1. So C1 would be actually determinant of, for ease of notation, let this thing be U1 and let this thing be U2. I'm just saving some brain space. So this is going to be determinant of U1 XA, U2 XB over the determinant of that thing, which is 1 XA, 1 XB. All right. So far, so good. So when I'm trying to solve for C1, I take this thing, I replace my first column with it, and I compute the determinant. So it's going to be U1 XB minus XA U2. Or let me write U2 XA. Same order. Over XB minus XA. Okay? So that is my C1. Now,
That's separate from that.
this is yes, this is something I've decided. So we got this. So what happened originally? We had the original equation, we multiplied it by the weighting function, integrated from XA to XB by parts. And now we're going to look for potential interpolation functions that we'll use to. I'll come back to I'll come back to this. So XB minus XA, XB minus XA, we can replace this with another symbol. Let XA equal H. So HE is pretty much the length of your element. You know, this XB minus this XA, that's an H. This XB minus this XA, that's an H. Just for keeps. We can do that. No problem. And so similarly, you can solve for C2. That'll be determinant of 1, 1, 1, 2 over one say 1 B. That's an H. U2 minus U1. All right? So I'll actually try this to compare. Who knows if I can screw this up or not. Okay. I did. Now, we also want to write this in a better form. We want to write this, we want to make sure that this looks, you know, very similar. So actually, let's rewrite this expression right there. Let's just plug in this C1 and C2. All right? So C1 we said is the U1 plus
Love it.
okay. Now we got our
No,
expression
staying in.
for an element. You can get your solution by using a interpolation function. Now, so this kind of looks very cumbersome to program. It's not meaningful. So we're actually going to take our C1 and we're going to write it differently. So C1 was U1 XB minus U2 XA write this in this form. I want to just take the h out, right? And I want to write it as lambda 1, alpha 1, u1 plus u2. Why not? What I'm doing, I'm just
Why did you change it? Why would you do that? Like, what was the purpose of that?
well, yeah. You will see. Let me finish C2 and I'll explain. It's nothing wrong with this. Easier to program. That's the little purpose.
What, instead of saying XB, you're going to say alpha?
Yes. I'll show you in a second. So C2 similarly, it was U2 minus U1 over H. I want to write this as 1 over H times beta 1 plus beta 2 times beta 1 and 1. Beta 2 U2. Now, why the hell did you want to do that? So, you can say that actually from here, kind of by inspection, such whatever, you can see that alpha I is 1 j x j e. Okay, where I and j no, don't be x j actually. Yeah, j.
Oh, it's alpha I.
Yeah, alpha I and JJ. Make sure. Okay. So the rule is if I is 1, then J is 2. If J is 1, then I is 2. So they permutate in the natural order. Does it make sense to everybody or not? So if, let's see, if I is 1, then, so let me just show you. If I is 1, then J is 2, and so alpha 1, that becomes negative 1 squared x 2, x2, and that becomes x2. So it works.
Is that X2 like in with XB? Like, is that the XB?
Yeah. X, you can say XB is X.
Would that work like that?
Right,
Okay.
right. So XA corresponds to X1. I know that this probably, this part right there confuses everybody because it seems like so weird and whatever. Like, why would you take the perfectly looking equation and turn this one? But the reason why it's done is because it simplifies the programming. That way you can have just one line. If you have to do this like 10,000 times, then it's just easier. It's easier. You can do this numerically rather than symbolically. Okay, so a little bit extraneous but necessary. And similarly, the beta I is negative 1 j. So if beta is 1, then it's negative. And beta is, so see, coefficient of 1 is negative.
-1 then
Okay, let's do it positive. I think that works. No, actually, hold on. I just screwed this up. That should be out. All right. So far so good. Is everybody good? Now, let's take this. And yet again, let's rewrite it using our alphas and betas. Okay? So u of x in terms of alphas and betas at any element is now 1 over h to the alpha 1. Okay. Now, in this form, it looks very more attractive to the eye because you got, alpha 1, U1, alpha 2, U2, beta 1, U1, beta 2, U2. You have this nice little thing going. So, this alpha and beta substitution was kind of necessary to go from, that clumsy form to something that is elegant and something that is very easy to program. So that's all there is to it. That's why it's being done. Is everybody good so far with this part? I mean, if not, please let me know because that's the one here. Yes.
Should the exponent I on the beta term be J? Beta 2
I is one that.
Oh.
No.
No,
I think it's
the
I.
user switched. Okay.
Yeah. What's the question? Okay. So, all right. Now that we have rewrote this thing, let's collect apples and oranges. Let's collect all of the coefficients that multiply U1s together and the coefficients that multiply U2 together, because that's a logical to do, right? So, U of x then 1 over HE, let's see, alpha 1 plus beta 1, U1. Beta x actually. Beta x. Plus alpha 2 beta 2 U2. All right, is everybody good so far? What I did, I just collected the terms. And now the next step is to call whatever multiplies U1 as E1, and whatever multiplies the U2, call it B2. All right? And these things, P1 and P2, we'll call them interpolation functions. That means that if you give me any x, the solution will be some portion of U1 and some portion of U2. So, like, if I give you a point U1 and if I give you point U2, and you want to find some value at any x, then it's fair to say that the solution will be, it'll be somewhere between U1 and U2, and you just interpolate. So it's some coefficient multiplied by U1 plus some coefficient multiplied by U2. That's the way you think about this. All right? Is everybody good so far? Okay. Now, let's keep this. All right, can I erase this? No. Okay, I'll start. Erasing probably this stuff. All right.
Be changing it.
All right. So here we are starting our problem again. Our differential equation, multiplying
true
it by
words.
weighting function W, integrating from xa to xb. Let's actually carry out this whole integration. So this chunk right here is going to be negative W u dx evaluated from xa to xb plus integral xa xb du dx dw dx dx. Okay? Now let's integrate this term. So you can split the integral. So that becomes integral from xa. Probably gonna erase this. Right.
I should have watched this.
Minus integral w q xa plus W squared. Okay, so what happened is that you have this integral what I did, you know, you can split this up. That's, you should remember this from your calculus. You can just, every term you can, you know, integrate it separately, right? So instead of writing this term, here I integrated it twice, well actually once by parts, and just left the other terms as is. Is everybody good so far? Yes? No?
Yep.
Okay, so that what happens. Now, this term right here, it can be rewritten as negative W times Q1 of X minus W Q2 of X. Again, you can rewrite this. You can make definitions. You can call, you know, Q1 to be du dx at let's say xp and this is at xa, and you can define this Q2 to be a negative of that. You kind of force the both terms to look negative again for the same reason you want it to look like this. And then so these are your like boundary terms. And then all of
Those
the
are
stuff.
boundary terms? Because he was calling them force terms at one point.
No. These are the boundary terms.
That's what we just did.
Yeah. And then you
I know
take,
it, but
then you take whatever integrals you have that feature u in them, and you call it Kij. Actually, hold on. Before you call it a Kij, what you're gonna do, you're going to take phi1, right? You're gonna let u equal phi1 of x, and you're gonna let w equals phi2 of x. So you're gonna just substitute those things in there. Okay? Everybody good? And if you rewrite this, I think I'm gonna be lazy and not write this, but these things right here, you're gonna call it Kij. And this thing right here, you're gonna call it Fj. So
How are you, they're saying that the derivative of the dw dx is equal to phi2. And over here, phi2 is referring to u2. How, I don't understand how you're related.
well, that's one of the mantras of the weighted residual method. So, no. The thing is, no. The thing is, look, think about it as is. What is this stuff? Du, if everybody can see it, du dx with respect to dx. That's from, take it from XA, take it from XA to XB, right? So that's going to be u evaluated at XA, XB, right? So without going too much into details, I mean, I don't have an easy answer to your question. I mean, that's the reason. If you just do the chain rule. Anyway. So,
You gotta look at the
when you
figure.
plug in your P1,
Trying to watch
P2
my
for
figure.
U and W, now you have an expression for Kj and Fj, and you can use that to actually solve for U at any point. Okay. Questions? I mean, you're lying. Okay. that.
We have plenty of questions. We just want to see you do the code because we're more screwed on that.
Okay.
Yeah, we'll have to say more.
Yeah, but a lot of people.
You got in trouble for that?
Well, no, not really, but a lot of people said that they don't understand the fundamentals. So if I give you the code, I mean that just.
Well, I mean, you can type it up on the screen and show us how it's done.
Yeah.
No pressure on it.
Okay, hold on. So questions.
I was just trying to understand, how do you get from one grade to another?
This is just.
It just means that.
That's just my last notation. So this is h of element, but h of element is the same because we define it the same. You don't have to. You don't have to take that into convention. Okay.
How'd you get the minus W21 XB minus W22 X?
Oh.
That's a good question.
So
Oh,
okay.
right there.
So this term, what you do, if you write it out, that becomes minus duw dx evaluated at xb plus w du dx evaluated at xb. So it's pretty much top minus bottom, but you've got a negative sign in front. So you also shift that, and then you make it look like negative w. You introduce this q variable so that it looks like negative w could be minus w. Actually, if you want to use xa. So you just say that let q1 du dx at xb and let u2 equals du dx at actually negative xa. You just make this substitution of variables to make this look like that. That will happen there. I think we have one more question, right? Questions? Oh, okay. So yeah, that's just another thing that you do so that things look pretty in the end. You can just make as many substitutions as you want. Okay. So for every element then, can I write the stuff on the right? Okay. Okay, now is the part where things are going to get a little bit fuzzy. Okay, let's go. All right, so Kij, right? What is that? All right, so you actually have to. All right. This term right here. Let's look at it.
You actually right after this. Like, kernel file? Really? Let's go learn to brainwash. It's just probably cold. Serious got lunch burger Monday though. What needs to happen?
All right. So now what you have to do, you have to just make a table.
Hashtag DJ. Yeah, someone else is on my water bottle. I let Sam drink it after he threw up yesterday, so I'm gonna wash it.
Okay, so now what you have to do, you have to plug in some phi for U and some phi for W. And integrate this out and see what you get. So for your choices, you have phi1 and phi2. So the first integral you can crunch out is where you plug in phi1 for U and phi1 for W. That's your first integral. Then you can evaluate that by hand or MATLAB. My purple MATLAB. Then you can plug in phi1 for U and then phi2 for W. Crunch that integral again, get a number. Similarly, do the same for phi2, phi1, phi2. You guys understand what I'm trying to communicate or not?
Yeah.
So you have this equation, just plug in these different combinations of phi1 and phi2 in there. And you crunch out the mathematics, you're going to have a number as an answer because XA is a number, let's say, for the first element it's going to be, XA is going to be 0, for the second 0.25, you get a number. So that's what we call. And so then you say, so if you let So if you let, let's say, U goes phi1 and W goes phi1, and you're going to get, call this variable k11, you're going to get a number. I'm just going to call it an A, just whatever. Then you let, let's say, U goes phi1 and W goes phi2, and then create a variable, call it, I don't know, k12, and let it be B. So, and you'll do the same for the other choices. Obviously, they will give you the same answer. Because, you know, it's just going to happen. And what we can
P21 or K21 will equal K12, right? Is K
Yeah.
yes,
K22 also
because
equals
right.
K11?
Yep.
So
That works out.
yeah, because look, that's one choice times the other choice, and that's one choice times the other choice. Order of multiplication doesn't matter. So that's why they're equal. So at the end of the day, if you put all your answers in the matrix, so you get your I'm actually going to have a different number here because if you let if you let U goes phi2 and W goes phi2 as well, that's going to be a different number. So I'm just going to
So K22 is going to be a different number?
yes, because it's going to be an integral of phi2 squared, essentially dx minus now phi2 rhymes. I'm just going to write it out. See that? So this is a unique choice, this is a unique choice, these two are pretty much the same. So is everybody okay so far or not? Please let me know. No. I'll explain. Or let's try it. All right. So you get a matrix like this, right, for your answers, and you call it K local. This is your local actual matrix. All right. Now, if you actually actually look at the way this integral is computed, it is really independent of XA and XB. And those of you who have the book, what time is it actually?
43.
Whoa. Okay, I don't have time to prove it to you, but it's a function of only of this coefficient, that coefficient, and the and H.
I know.
So, if you're really curious, let's just quickly write this equation.
Oops.
But anyway, the point that I'm trying to make is that this k local, the answer that you're going to get for the k local matrix will be the same if you take the first element, the second element, the third, and the fourth. Even if you're discretizing your elements to be equidistant from each other. If you look at the expressions, let's say for one, you can kind of see that. But anyway, so all right, we have our k local matrix. Now what? What do we do? Well, can I erase this up? Okay.
Yeah, your K local matrix should have like the same.
Same one.
I think if you do K22, it ends up being the same thing.
Yeah.
It's K11. If you plug in everything in, you have to go all the way back to the thing and plug in everything.
Right.
To get it from, I think
Right,
it's
right.
at the end.
And the reason why it's the same because look, that's what you're integrating. That's one choice times the other, one choice times the other.
Yeah.
That's like, you know, fine. I'll write it like this.
Yeah.
Well,
No, that, I'm saying that the K22 would equal K11.
yeah. Oh, k to 2, k1.
Yeah.
Because we have it in our notes that it's like.
Hold on, k1 2, k2 1.
Yeah.
And K11 and K22. We have the same thing, because our matrix comes out to be like A over H, 1 minus 1, minus 1, 1, and then 2, 1, 1, 2, which is just saying that. So, I mean, I guess we should just not take that for
I mean,
truth. I was just taking it as truth. I wasn't really like.
it may turn out to be true. I wouldn't bet on it, but it may be true. I wouldn't bet on it. I will actually be able to tell you later. I can take a look at a book and you know, if that's shown up. Anyway, so, all right. Now let me make this sketch. All right. So here's our again domain. We've got one node, two node, three node, four node, right? Okay, note my notation. So what I have an X, I have a subscript and a superscript. The superscript indicates the element to which the value belongs. So this is element 1, so you got XA1 and X1B, right? And subscript represents which endpoint it is. A meets 1, B meets 2. Everybody is okay with this? All right. So, but, all right, now you know that this point right here, this point is a global node number 1. This point right here is a global node number 2. This node right there is a global node number 3. Now, note that X, B, 1 is XA2. Everybody agrees? Everybody go with me? All right. So we want to. So for every element, you can write out two separate equations that govern it, right? One in terms of U1 and one in terms of U2. So if you go through all this work and if you equate the equations, you can put this in a global matrix. And so since we have 1, 2, 3, 4 elements, you will need a 5 by 5 matrix. No, actually, do I want? Okay, so if you have 4 elements, you need the 5 by 5 matrix because you have 1, 2, 3, 4, 5 nodes. Now, so this is your global K, and you're multiplying it by capital U1, capital U2. You're going to put a bar over U so that it means global. Okay. So if you look at your local K matrix for element 1, right? You can park this matrix right there. So K 1, 1, 1, K 1, 1, 2, K 1, 2, 1. Okay. Is everybody good with this step or not? Do you guys know what just happened?
Yeah.
So this is actually equivalent to, if I fill everything else here with zeros, this is equivalent to K11, K12, K21, K22 times U1, U2. So that's my definition of my local matrix right there. All right, so that's equivalent. Now, we did the first element, now we take the second element. Where do we put it? We have to assemble the global matrix. Well, the second element hits nodes 2 and 3. So whatever I put better, give me a value when I multiply by 2 and 3. And I also know that XA2 overlays with XA1. So I know that I need to be in these two rows right here because my equations are in terms of U2 and U3. And I also know that I'm overlaying with X1, so I would pretty much park my K global matrix. So, actually, over here,
That's gonna be my new pen name.
all right, so guys, do you see what happened? Here?
Yeah.
No,
It's gonna be plus K.
So actually, if I wanted to start with my second element, I would have this 5 by 5 matrix. 1, 2, 3, 4, 5. 1, 2,